Welcome to Astronomy State of the Art. It's another one of our live sessions. The floor is open for questions on anything to do with the course or anything that's happening in astronomy and astrophysics.
So this was actually asked just at the last minute in our last live session. We're just getting to it now, and it's from Bob. And Bob asked, how are we seeing the light radiation from the Big Bang? If I go out at night and shine a flashlight up to space, that light travels up till I shut the light off. Then only what was shown travels on. The Big Bang lasted only a second.
A good question. Yeah, how do we see light from the Big Bang or radiation from the Big Bang, to be more general about it? That's right. If you just shine a light out into space for a limited period of time, that beam of photons travels through space, and we think because space is flat, it would never return. So photons sent out into space from the Earth will just travel endlessly through space. So how can we see light from an event, or radiation from an event that took place 13.7 billion years ago? So the situation to think about is that the creation of the universe was a creation of all time and space in one instant. That's immediately a little unintuitive, because how can, it begs the question of, was there an expansion into something? Was there anything outside? And the simplest way to answer that is to say that within the theory of gravity that explains the Big Bang, general relativity, there's no need for a container. The Big Bang, conceptually and physically by the equations, does not need to occur within a larger situation. So space-time is self-contained in the Big Bang, probably highly curved and extremely dense and high temperature. And the unfolding of space and time since the Big Bang is the totality of space-time that we have access to. So that's everything we see was once in a tiny region at a very, very high temperature. So if the totality of the universe was once at this very high temperature, the totality of the universe had a very high radiation temperature. And so the universe would have been filled with intense gamma radiation at the very beginning, even beyond gamma rays, just the very highest energy radiation you can imagine. As the universe expands, it cools, and the radiation within it continues to travel at the speed of light, as radiation will through a vacuum, but diminishes in energy. And it diminishes according to the expansion itself. So redshift is essentially a measure of the expansion of space-time. If the universe gets 2 times bigger, the waves traveling through the universe get 2 times longer, and that means the energy of those waves is going down by a factor of 2. So what was initially gamma rays is going to reduce towards lower wavelength radiation. If you then work the equations to how much the universe has expanded since the Big Bang, it's an incredible factor. But the best signature we have of the Big Bang is the radiation that started to travel in free space without interactions as the universe cooled to the formation of stable hydrogen atoms, that is, electrons attaching to protons. That's called recombination. And at that point, electrons are not scattering photons, the photons travel freely, and that's our sort of picture, looking backwards in time and out in space in every direction of the Big Bang. The temperature at that point was 3,000 Kelvin, so the entire universe was the temperature of the outer edge of a cool star, shining, if you like, in very dull red wavelengths of light. Since that time, the universe has expanded by a factor of 1,000, and so those red photons have expanded by a factor of 1,000 to become microwaves. And it's the microwaves from that epoch, which was 400,000 years after the Big Bang, that we see with radio telescopes. And that was the signature of the Big Bang in 1964 that convinced scientists that that was a valid theory for the formation of the universe. So it was a simple question, but it has a complex answer, because the radiation from the Big Bang permeates space-time, all of the universe. There's nothing outside it. That's an unnecessary concept, although it's almost irresistible to ask that question. Well, what's outside? What is it expanding into? The concept of the Big Bang does not require an external container or an external medium. There's no expansion into anything else. And so space-time around us is filled with the same radiation that was always there. It's just been cooling as it travels due to the stretching of space itself. And now we've seen evidence of that radiation, or first time actually 40, 50 years ago. So that's the radiation from the Big Bang, and it becomes very compelling evidence that the universe was once very hot and very dense.
Priyanka asks, can you clarify on the latest results by the Planck Satellite? There was an announcement a few months ago regarding the so-called axis of evil. I don't know if I got this right, but can you please explain?
The Planck results, it's actually, unfortunately, too early to draw a line under Planck, and the teams reporting results are being extremely cautious in drawing profound conclusions. And I think they've been influenced by the possible misstep of the result from the South Pole, which claimed evidence for inflation, actual evidence for inflation. Now, that's been the subject of previous questions in previous weeks, so I'm not going to go over that again. But interpreting microwave radiation at a very fine level, like tiny fractions of a percent, is really tricky. People are always pushing the data, and they want to see smaller and smaller effects. So one of the things Planck is doing is trying to cross-check the results on the microwave background polarization, which was evidence for inflation claimed a few months ago. And so far, they've not seen evidence of that signature. They've actually seen that the dust signature of our own galaxy, which sort of contaminates the microwaves because it's a foreground signal, is actually confusing the situation. Axis of evil and other sort of acronyms or tags given to results that are pending refers to departures from homogeneity and isotropy. So one of the premises of cosmic expansion is that it doesn't matter what direction you look, you see the same thing. The expansion rate is the same in all directions. There's no special place in the universe, and we're certainly not in a privileged position. That's isotropy. Homogeneity says that if you transport it to a different location in the universe, you'd see roughly the same things. You'd see galaxies moving away from you, a Hubble expansion. There's no privileged position again. Well, the new satellite, Planck, is able to test homogeneity and isotropy, especially isotropy, at a very fine level. And of course, people do see slight departures in the microwave intensity and the pattern of fluctuations in different directions. And the question is, are these differences from one direction and another significant and evidence that this cosmological principle that really underlies our model is wrong? Or are they just fluctuations? Every now and then there can be a fluctuation and it might mislead you. And the axis of evil result, if you like, it's not really a result, is a hint that there's something weird in some directions in the sky. And I think based on all the results of the last decade or so, we should be exceptionally cautious about interpreting this result. People, of course, are making their reputations, they're trying to get famous, they want to publish papers, but all the evidence of the last decade, and especially the last 6 months, suggests that we should be very cagey about accepting these results. At the moment, the Planck data is supporting the Big Bang model at a new high level of precision.
Right. The next question is kind of a building on the same thing. Talking about Planck Satellite, I heard that if an imaginary axis were drawn between the universe and divided into two hemispheres, you'll get a hotter region in one, a cooler region in the other. And then the question goes on to say, can you please clarify, does this look like an intentional design by some unknown source, or does nature behave this way and that this is normal?
So that aspect of the microwave radiation is completely anticipated and has actually been measured back since the Kobe satellite in the late 1980s. So the difference in the temperature, slight difference in temperature from one hemisphere to another, is called the dipole signal, as a magnetic field has a dipole, a north and a south pole with different field line directions. So the sky has a slightly different temperature. It's about 1 part in 1,000 hotter in one direction and 1 part in 1,000 cooler in the other direction. And that's a dipole signal, and that's what the question is referring to. That is not a problem, and that's not evidence of a problem in the cosmology. That's actually something that we completely expect because of this. The Milky Way is not at a rest with respect to the larger universe. The Milky Way is in gravitational interaction with Andromeda. We're falling towards Andromeda 100 kilometers per second. And the Milky Way and Andromeda and the entire local group are falling into the Virgo cluster. The Virgo cluster is part of a very large concentration of galaxies called the local supercluster. So we see that the Milky Way has motions with respect to very large concentrations of matter in our proximate universe, and by proximate I mean 50 to 100 million light years away a volume encompassing tens of thousands of galaxies. So we do in fact see the infall of the Milky Way. We see the motion of the Milky Way with respect to these much larger aggregations of galaxies and therefore mass. And that amount of motion is represented by the dipole. It's that tiny 1 part in 1,000 difference in temperature. It's going to be, it's a little, the wavelength is a little shorter or bluer in the direction we're moving, and a little redder or longer in the direction away from which we're moving. And that amount of motion was first measured a couple of decades ago, and it's been measured with beautiful detail by the Planck Satellite. So there's no problem there, there's no surprise there, but it's a beautiful measurement of this dipole effect. And of course, what we expect and anticipate is that if you look on the very largest scales, obviously there should be no net motion. It's quite okay for one galaxy to be moving with respect to the larger universe. But when you eventually look at volumes containing tens or hundreds of thousands of galaxies, there should be no reason for them to be moving with respect to the entire universe or billions of galaxies. And that's indeed what we see. So the motions that are detected in this signal are very local motions based on the Milky Way's motion with respect to nearby galaxies. If we could draw a bigger circle around the Milky Way, we would find a very large set of galaxies that are not moving with respect to the universe at large.
Okay, so we have 3 questions that are all revolving around the concept of dark energy and dark matter. So I'll go through the general ideas. So how does dark energy work? What is the relationship between dark matter and dark energy? I heard that it has to do with negative energy. Is dark energy a constant, or does it vary? And what is new in the study of dark energy?
It's good. These are all good questions because dark energy is the biggest enigma in cosmology. It's plain and simple. It's a thing we don't understand. It's also an enigma of physics because physics provides no insight into what dark energy is. So I should just start with a simple statement of fact, which is that we don't know what dark energy is, period. Okay, so anything beyond that is speculation, and there's plenty of speculation. So what do we know and what don't we know? The evidence for dark energy came from the measurement of the accelerating universe in 1995 by distant supernova measurements. So we think that the universe is accelerating, we're confident of that result, and we ascribe that acceleration to an entity which works opposite gravity. And so there's the negative, there's the idea of negative pressure, the fact that that whatever is filling space-time and causing accelerating expansion must work in opposition to gravity. And physically that means it has the property of negative pressure. So that's one of the things we know about dark energy, but that doesn't enlighten us, that doesn't tell us what it is physically, because we don't know of anything that works opposite to gravity. That's actually a real problem. We know that there could be energy in the vacuum of space. Physics provides mechanisms whereby particles and antiparticles can come and go from pure vacuum on very short timescales. As long as they disappear, they're allowed to violate conservation of energy for a very short time. That's a quantum principle. So we have a mechanism for energy in the vacuum of space, but that mechanism in physics does not explain why the universe is accelerating. So it's a failure. It essentially means we don't have the right physics. So we're coming up dry, mostly. The evidence of something causing accelerating expansion is secure. That's been confirmed by multiple groups. But the nature of the physical entity is not clear. Now, one of the questions which is very important is, does dark energy, or whatever entity is causing accelerating expansion, does it vary with time and space? That's a very important question to ask and answer. Dark matter, for instance, we've now mapped out. And so we know how dark matter is distributed in the universe. And it is indeed distributed into the spaces between galaxies. But because it has gravity, it clumps according to gravities, just not as strongly as galaxies. So we made maps of dark matter, and we know that dark matter varies across space. And we also know that dark matter varies with time, because gravity has made dark matter clump more and more as the universe ages. So we expect, and even have measured, that dark matter was more smoothly distributed in the distant past. So on dark matter, we actually do have evidence or measurements of the variation in time and space. What about dark energy? Again, much, much less information. Einstein's cosmological constant, which you've probably heard of, which is one way of mathematically associating an entity with dark matter, dark energy, sorry, that cosmological constant was assumed to not vary over time and space. That's the simplest possible way you can put it in an equation with general relativity. And so far, the observational evidence is consistent with that. In other words, we've seen no indication that dark energy varies, for instance, in one direction of the sky or the other. The accelerated expansion is the same wherever you look. And then much harder, however, is to judge whether dark energy is varying over cosmic time. We're just not quite clever enough to make experiments over the change in dark energy over cosmic time. Supernovae, the same objects that allowed us to detect accelerated expansion in the first place, they do give us a little handle on that. And so far, supernova results mapping back over about 3/4 of the age of the universe don't show any sign of dark energy changing its strength over that time. So far, we have a null result. We have indication that dark energy does not vary in space or in time, and so it behaves like the simple entity of Einstein's cosmological constant. Behaving simply like that actually is slightly frustrating because it doesn't give us a handle on what dark energy is. If it had more interesting or complex behavior, it might actually help us understand it. So at the moment, we don't know what it is. Physicists are developing various theories to try and explain it. Astronomers are trying to develop more advanced techniques to measure dark energy in more detail, but given its very simple behavior in terms of how it controls cosmic expansion, it's really hard to develop new experiments to understand dark energy.
All right, the next question is from Adarsh. What is the relation to time?
So space and time in Newton's theory of gravity were completely independent and unassociated, unrelated. And that almost makes intuitive sense. Space is something where objects exist in space, the planets move through space, people occupy space, the universe has a volume and consists of space. And time seems to be something completely different. Time, of course, to humans has a psychological component, but time is something that flows and never rewinds. It moves forward in one direction, and it just has attributes that seem completely distinct from space. So Newton's understanding of time and space is sort of the intuitive understanding that we have. That space and time are completely distinct concepts or constructs or physical entities, and there's really no relationship between them. We can say that that events in the universe occur in space and in time. They occur in a particular location and at a particular time, but that in itself, talking about events, does not relate space and time. General relativity was a remarkable theory of gravity by Einstein, because the formalism for general relativity directly couples space and time. So it's built into the mathematics of general relativity that space and time are linked, intimately linked in the equations. And that means physically linked too. Now, in situations of weak gravity, like the terrestrial environment, the solar system, most regions of the Milky Way, most regions of space actually, space and time are not linked in a way that creates anything interesting going on. But in general relativity, when the gravity is strong, then the coupling of space and time leads to some very interesting effects. And we've seen evidence of those effects with black holes and neutron stars. The most obvious of these effects is that time runs slower in an intense gravitational field. So there's a direct coupling of space and time, because in a physical region of space where the mass density is high, a clock runs slower than in a lower region of space, a lower density region of space. So that's something completely unanticipated in Newtonian gravity. That was a prediction out of general relativity way back from 1916, and it was finally experimentally verified some decades ago, as soon as we got accurate atomic clocks. Basically, you just take two atomic clocks, have one on the Earth's surface, and fly the other one in a high altitude in military plane. It was actually done by the US military in the 1950s using maser atomic clocks. And what happens is you have two identical atomic clocks keeping perfectly precise time, each the same. And you take one and fly it around at high altitude. And the only difference at high altitude is the gravity field is very, very slightly weaker than the Earth's surface. And I mean very slightly, it's like a few parts in a trillion. When you eventually bring the two clocks close together, you find that the stronger gravity field on the Earth's surface has slowed down time slightly. And so the clock that was left on the Earth's surface is running very, very slightly slower, a few parts per trillion, than the clock that was flying in the aircraft. Since then, very similar experiments have been done many times, and they demonstrate convincingly that time runs slower in a stronger gravity field. In fact, the most recent example of this experiment, quoted in the journal Nature just this year, this summer, was an extraordinary experiment. Now the atomic clocks are so good that you can actually detect the slowing down of time within the laboratory. So they literally had two super accurate atomic clocks, and one was just a meter or so above the other on the Earth's surface. And they were able to detect the slowing of time from the clock that was lower than the one that was higher. That was an incredible experiment. So this is absolutely convincing demonstration that general relativity is correct. So there is a direct coupling of space and time that is unpredicted by Newtonian theory, that is predicted and understood by Newtonian theory, gravitational theory of Einstein. And the extreme version of this, of course, is the event horizon of a black hole, where if you believe the equations of general relativity, time would slow down infinitely. In other words, time would essentially stop at the event horizon, where the gravity field is so intense that regions within that disappear from the visible universe. So that's an extreme manifestation of this phenomenon. And astronomers, of course, are hoping to find regions of space where we can look at stars, say, passing very close to black holes, where we might be able to diagnose this very radical change in time near the event horizon of a black hole. That would be extremely exciting. And actually, people are dreaming of experiments where we might do this within a decade.
The next question is from Janet, and she asks, I understand that the lifetime of a Higgs boson is 1/septillionth of a second or 1/sextillionth, depending on the source of information. My question is, does the Higgs boson decay into 2 tau particles?
That is a decay channel of the Higgs boson. It's one of the more, perhaps the most abundant decay channel. And the tau particles themselves are unstable, so there will be a series of decay products. And in fact, if you reverse that logic, because any subatomic particle interaction that moves in one direction can be made to go in the opposite direction, given suitable conditions, then that, of course, becomes a path by which you can create, in an evanescent and temporary way, a Higgs particle. So yes, the Higgs is unstable. One of its decay paths is as you described, but it has other decay paths and therefore also other ways of being produced. So when people are trying to generate a Higgs particle, they basically create a huge train wreck of particle collisions of sufficient energy to manifest the Higgs particle. We know what its energy is. And then they look for this signature of a pathway which only the Higgs particle has and other particle interactions don't. Well, when you have that kind of phenomenal energy at play, just raw energy to create particle-antiparticle pairs and various decay products, it's a mess. You have a whole zoo of particles that you can create that all come and go. Many are unstable and decay into their own secondary and tertiary products. So that's why the detection of the Higgs was a tour de force. It was a masterpiece of experimental design, because the collisions that created it and then its very short lifetime before it decays is just a blip on the radar of a very complicated high-energy physics experiments with thousands and thousands of different interactions going on. And it almost sounds impossible, but of course it took groups, thousands of scientists strong, a couple of years to be convinced of the results. So it was a phenomenal amount of work that led to that result.
So Priyanka asks, are we any closer to finding super-symmetrical particles at the LHC or any experiments on the International Space Station? Are there any hopes of finding this when the LHC starts running at 14 TeV?
At this point, no. The last run of the LHC produced no hints of supersymmetry, and that was very disappointing. It's actually become a talking point in high-energy physics circles. The corridors of physics departments are abuzz with the absence of any signature of supersymmetry. LHC already should have seen some lower energy LHC cannot, of course, create the temperature where supersymmetry is completely manifested. All it can see is much lower energy hints of supersymmetry in operation. But we know that's a plausible way to look for a symmetry principle, because in the 1970s, the electroweak, the unification of the weak and the electromagnetic force, was demonstrated also at CERN at a much lower energy than the full merger of those forces. So the precedent for looking for supersymmetry is already there from this physics of 40 years ago. The absence of any supersymmetric hints is disappointing, in that it's already ruled out a number of the more elegant and simple supersymmetry theories. And the jury is essentially out on whether that leaves the whole theory, the whole idea, in disarray or a problem. Because, of course, there was never just one supersymmetry theory. There were dozens of supersymmetry theories, of variations. And it's clever. It's Byzantine physics because it's new physics. You're hypothesizing a shadow set of particles that unify fermions, or half-integer spin particles, with bosons, or integer spin particles. And so that creates a rich phenomenology of interactions that can only be seen at these very high energies. When the LHC comes back at yet higher energy, it's not a dramatically higher energy, but it's high enough energy that, again, supersymmetry hints should be visible. And in fact, you predict more of them as you go up in energy. You should start to home in on the effects of supersymmetry. If the next LHC run comes up completely dry, shows no hints of supersymmetry, then the number of models, or the fraction of plausible supersymmetry models that will be ruled out, will be really substantial. I think most physicists think that if LHC sees nothing in a year or so, then supersymmetry is on the ropes. The whole idea is sort of in some deep form of trouble. And physicists will have to be looking a little deeper into nature to understand what's going on. And depending on your perspective, that's a good thing or a bad thing.
Next question is from Janet. The distant matter of the universe can instantaneously act upon a moving body here on Earth, also known as Mach's principle. Can you explain further?
Good question, because Mach's principle was of strong motivation to Einstein in his thinking about gravity. Mach was a contemporary of Einstein, but somewhat older. He was really a physicist of the 19th century rather than the 20th century. And his thinking was important. And his thinking, of course, echoed an issue that Newton was well aware of, which is when Newton was asked by one of his colleagues, how does this magical force of gravity operate instantaneously across the vacuum of space with nothing to propagate it? Newton famously said, "I frame no hypothesis." He meant he didn't know. He had a physical theory of gravity, thinking of it as a field operating through the vacuum of space, indeed, at the speed of light, actually. So in general relativity, gravity is presumed to propagate at light speed. But Newton had no way of testing it. Einstein's theory, as I mentioned, hypothesizes that there is a particle transmitting gravity called the graviton. The graviton has never been observed. Gravity should propagate at the speed of light. Experiments to test the propagation of gravity have been attempted. They're extremely difficult because, of course, as you can imagine, in the universe, especially in the larger universe, you can't just switch on a mass. It's very hard to create instantaneously a new mass. You can redistribute matter, you can blow things up, stars merge, supernovae blow apart, but it's very hard to actually suddenly put a pulse of matter into the universe. And so it's therefore very hard to test the idea that gravity propagates at the speed of light, but that's built into general relativity. So it's an untested part of general relativity. And Mach's extensive version of that idea was, how does the universe must operate as if the distant matter, the universe knows about them. All the mass in the universe is acting on all the other mass in the universe. Obviously, the universe is not infinite in age. So how can that be? How can the universe, one far off part of the universe, be aware of the gravity of another far off part of the universe? And that is almost a philosophical issue or question that was not fully resolved by Einstein. However, Mach's thought, his thought experiment, his question motivated Einstein in his theory. And so it's important that that part of Einstein's theory has never been put to the test. If you hypothesize that that's wrong, that gravity somehow propagates or manifests instantaneously across space and time, then you have another difficult problem. Well, how can that be? because that's acausal. That's violating causality, which is a really foundational principle of science. So this is a good question because it's still a conceptually unresolved issue of physics, and it's unresolved experimentally too because the measurements are so difficult.
Right, the next question is from Spencer, who asks, what is the state of the art regarding gravitational waves?
Gravitational waves are, you know, we're waiting for LIGO. LIGO is due to come back in its full science operating phase. You know, the time keeps getting put off a little bit. They've had their test phase. They satisfied all their science requirements. They've upgraded the detectors. And I think we imagine it's going to be mid next year, mid to late 2015 when LIGO goes into science operation phase. If it attains its design sensitivity, we pretty much should hear weekly press releases of gravity wave events detected by LIGO. It will be a surprise if that's not the case. So basically the whole game of gravity waves will be on sometime in probably late 2015, given how these things go, which is very exciting. It's a brand new field of physics and astrophysics that's going to open up. Outside of LIGO, there are other gravity wave experiments. In fact, LIGO, of course, is not unique. LIGO has a twin. LIGO exists at two places, in Louisiana and Washington State, and a third gravity wave detector is being built in the Mont Blanc tunnel in the Swiss Alps by the Europeans. So there's a trio of very sensitive gravity wave experiments, and there's actually now a couple of other gravity wave experiments that are being planned in other parts of the world, not quite with the sensitivity of LIGO. The LISA experiment, which is a gravity wave interferometer in space, sensitive to very low frequency gravity waves, which means very massive compact objects like supermassive black holes. The design phase for that was successfully completed some years ago, so there are no showstoppers in building such a device. The showstopper is essentially money and NASA's budget. NASA would need several, probably $3 or $4 billion to get that project going, and most people think it would end up costing more than that, maybe like JWST, 7 or 8 billion. And that's a lot of money to put into a very esoteric science experiment, and it's unlikely the public or NASA's constituencies will unify enough around the LISA concept for LISA to happen. So a lot of people don't expect LISA to go up. Other than that, our gravity wave experiments are the indirect kind. They involve typically binary pulsars. So the situations of the strongest gravity are compact stars orbiting each other, neutron star pairs or pulsar pairs, and neutron star black hole pairs. Black hole is also possible, but it's very rare because black holes are so rare. And those situations where the pulsar is a superb clock, of course, give you the best handle on the gravity physics. And in fact, Hulse-Taylor won the Nobel Prize about a decade ago for observations of the binary pulsar that indicated the coalescence of that pulsar due to the emission of gravity waves. So before LIGO, a Nobel Prize was awarded in physics for the indirect detection of gravity waves using pulsars. And those pulsar experiments continue. Pulsar physics is very well understood. The number of pulsars has grown to 5,000 or 6,000. And we found a significant number, a few dozen of these binary pulsars. So for the moment, and until LIGO hits its stride, binary pulsar experiments are a very interesting way of understanding gravity waves. There's no doubt that they exist. I think even though it's indirect detection, it's a pretty compelling experiment. It'd be very hard to explain those binary pulsar observations if gravity waves didn't exist.
In one of the lectures, you mentioned that in the past few billion years, quasar activity peaked and then declined. Does this mean that black holes are not that active nowadays, since quasars are the observed phenomena of a black hole? And please clarify.
Yes, absolutely. Very good question and correct inference. Quasar activity peaked at a redshift of about 2, which is when the universe was 3 times smaller than it is now. That's about 2/3 to 3/4 back in the history of the universe, so about 4-ish billion years after the Big Bang. And the Big Bang was 13.8 billion years ago. So the more general question is, why is there a curve to quasar activity? Why did quasar activity rise, peak, and then fall dramatically? What causes that? Given that the universe has just been expanding continuously since then. So that's an interesting thing to explain. And I think we understand it in general terms. We first of all imagine that every galaxy has a black hole in it because we observe that in the local universe. Every galaxy has a black hole, and the black hole scales with the mass of the galaxy. We also imagine, since galaxies were assembled by sequential mergers, that the black holes grew by those same sequential mergers and by more steady feeding of mass within the galaxy. So we expect black holes to systematically grow in size, maybe at different rates, but they should continuously grow. So both galaxies and their contained black holes will grow continuously through the universe. So again, that has not explained why quasar activity should peak and then fall. The simple answer is that there was a period of high degree of coalescence of galaxies. So galaxies did go through a very active phase of mergers and star formation. And that's because the universe, when it was 3 times smaller, was 3 cubed or 27, 30 times denser. And so there was a lot more material. There were a lot more interactions. There were a lot more mergers. There was a lot more raw gas available for growing black holes and for feeding them. And some of that gas would turn into stars, but a lot was available to feed the central black hole. So nuclear activity went through a very rapid rise because galaxies were merging, their black holes were growing quite quickly, and there was a lot of gas around for them to be fueled. And there were a lot of interactions and mergers, and the mergers and interactions also help with fueling. So that's why you get a rise in the activity. Why does that plateau and then fall? Because of the continual expansion. So eventually, as the universe expands, the number of interactions and mergers of galaxies starts to decline, because even though galaxies will encounter each other and can be held together by their mutual gravity, on average, they're moving further apart. So the probability of encounters or interactions or mergers goes down very steadily, and at some point, they just stop happening. And so as galaxies become more isolated in the expanding universe, their source of new fuel diminishes. All they have is their internal reserves of fuel. And since that fuel is being used to create stars, and those stars will die and leave stellar remnants and only eject a fraction of that gas back into the galaxy, the gas supply is going down. So your supply of gas for either your merger supply for growing galaxies or your gas supply internally or externally for fueling a black hole is diminishing. So the black holes you've made are not shrinking, they can't shrink, but they can be starved. And in fact, that's what we think is happening. And so since the peak of the quasar era, which was about 7 or 8 billion years ago, quasar activity, which is to say the sort of density of luminous quasars in a cubic gigaparsec of sky, has gone down by a factor of about 1 or 200. Quite a lot, several orders of magnitude less quasar activity than there was 8 billion years ago. And that is pretty neatly explained by the lack of mergers and the lack of raw material to fuel the quasar. So we have a larger fraction of these massive black holes that have been built by galaxies in this sort of starved phase. And what we think happens is that these black holes, since every galaxy has a black hole, they're active some fraction of the time, maybe only about 1%. And so if you looked at 100 nearby galaxies, you'd only ever see one of them in a quasar phase, on average. We think that duty cycle, as it's called, was much higher 8 billion years ago, whereas if you looked at 100 typical galaxies 8 billion years ago, more like 10 or 20 of them would have been in the active phase. So that is what we think has happened, and so the quasar activity era is long past.
So the next question is from Stanley. Will MAVEN provide useful data that may aid with any future plans to terraform Mars?
Possibly. MAVEN is designed, MAVEN is a Mars orbiter whose science goal is to determine the history of the Martian atmosphere. Why did Mars lose its atmosphere? So we have hypotheses on the table that present Mars as being a potentially habitable planet 3 billion years ago, which means that it must have had surface water, because we see evidence for previous surface water. And that in turn means that Mars must have been warmer in the past, warmer because now liquid water can't exist, it's too cold, and it must have had a denser atmosphere. The other reason liquid water can't exist on Mars is the atmosphere is so thin that the water you put there would both freeze and evaporate, would essentially boil off. So MAVEN is designed to give us indication to gather evidence to account for the history of the Martian atmosphere, which is really answering the question, is there indirect evidence that Mars did have a thicker atmosphere, apart from the fact that we think water existed on the surface 3 billion years ago? And more particularly, because it's a measurement that can be done right now, what is the rate at which Mars is leaking its atmosphere into space? And so if you measure the leakage rate of the atmosphere now, you can run that clock backwards and infer how much of Mars' atmosphere has been leaked into space over a couple of billion years. That's an important experiment. Why does Mars leak its atmosphere? Well, all planets leak their atmospheres. You basically can do a simple calculation for any chemical element or molecule. You can take the temperature of that molecule and work out what the RMS velocity in a gas of the collision speed of those molecules are. That's just a simple Boltzmann of thermal physics calculation. It's freshman physics. And if you do that calculation and that RMS, root mean square, or typical velocity of the molecule is higher than the escape velocity or similar to it, then that constituent will gradually leak out of the atmosphere. Obviously, the more massive the molecule for a given temperature, the slower it's going to be moving, because kinetic energy is half mv squared. And so that means that light gases will escape more easily than heavy gases. Carbon dioxide and carbon monoxide and oxygen and nitrogen are pretty heavy gases, so they'll be the slowest to escape. Hydrogen and helium will be the quickest to escape. So MAVEN is going to make very careful measurements of the stratigraphy, or the temperature and density profile of the Martian atmosphere and the physical conditions within it, the temperature throughout the Martian atmosphere, and put real meat on the bones of this idea of how atmospheres evaporate into space. And if it does its job well, it will either affirm the idea that the Martian atmosphere has been leaking in a way that, running the clock backwards, it could have well been thick enough to hold water on the surface and possibly life on the surface 3 billion years ago, or it won't affirm that idea, in which case we're going to have to look around and figure out what was going on with Mars. It means we won't understand Mars as well as we thought. So it's a pretty important mission.
And that's the last question for today.
Okay, it's great questions. Everything from Mars to dark energy, which I like. I like to cover the ground, and I hope you all continue to enjoy the class and participate in our live sessions, which we'll keep having every few weeks. Thank you.